Welcome to the afternoon session. It's a pleasure to have Laura Balzano with us, and she'll tell us about how to optimally weight PCA.
Great. Thank you very much for the introduction. Thank you also to the organizers for the invitation. This workshop has been really excellent. I've learned a lot this week, so I appreciate that opportunity. Today I'm going to tell you about work on PCA for high-dimensional heteroscedastic data. My idea of heteroscedastic data is going to be that different columns in my matrix valued data set have different levels of additive noise, different variances. And I'll tell you then about how to weight PCA in order to get an optimal recovery guarantee in the asymptotic regime. So this work is work of my PhD student David Hong, who is here in the audience. So if you're interested, he has a lot of interesting things to tell you about it, and joint with our colleague Jeff Fessler at the University of Michigan. Okay, so first I want to motivate the problem that we're interested in. We work on high-dimensional data problems where we often have very large data sets, not only with many variables, but sometimes with more variables than number of samples that we observe. Applications that we think about and are interested in include in medical imaging, where we take images with many voxels of interior of a person's body, or in astronomy, where we have very, very large detector systems trying to sample the sky, and in sensor networks, environmental sensor networks, where we may have many, many sensors spread out through a space trying to understand some environmental phenomena. And it turns out in all of these different applications I've mentioned, we also have heteroscedastic data, or data of different quality. So in the medical imaging scenario, for example, which was one of the first things that motivated us to think about this, there are often scans that are taken at different levels of radiation. And so the signal-to-noise ratio you get on some scans is different than on other scans. And we would like to be able to learn something from all that data at once, instead of trying to infer just from each subset of the data. In astronomy, different data points have different noise variance because the atmosphere changes depending on the evening that certain measurements are taken. And in sensor networks, there are very often high-quality weather monitoring stations that are carefully calibrated and that noise level can be controlled, but other very low-quality sensors that have much higher noise. So in all these cases, we would like to be able to learn from all the data together, but because of the different noise levels, we need to do something clever in order to handle that. Okay, so let me tell you about the model that we have that underlies all of our results. We have n samples in d dimensions, and each one of those samples is generated as a draw from some subspace weighted by amplitude. So this U is a k-dimensional subspace. This theta is a diagonal matrix with some amplitudes on the signal. And then we get some IID random draw from that subspace. Then we have additive noise, where we think of each noise vector as being standard, being IID and mean 0 variance 1, but then the standard deviation can be different from column to column. We have, say, some number of samples with each noise variance, and we'll use capital L to denote the number of different types of quality data that we have in our data set. And so our goal will then be from, for example, this data with two different quality data set to learn the underlying subspace U, okay, this green line that's generating them. So this type of problem has been looked at quite a bit in the context of unweighted PCA and homoscedastic data, where we think of exactly this model, but with all of these noise variances the same. And in particular, there's a now long line of results over the past 15 years looking at the asymptotic behavior of the recovery of the first principle, or excuse me, of the underlying principal components using the principal components from PCA. Okay. So what this says is that the principal component from PCA has an inner product with that underlying component that converges as n and d grow to infinity, but with fixed ratio c. So let me write that on the board. So n is the number of samples, d is the dimension, and n over d goes to c. So as n over d grow, but going to this fixed ratio c, we have recovery that looks like this, where we have a ratio of two terms. That in the case where there isn't noise goes to 1, but otherwise is something less than 1 because of the additive noise in the model. Okay. Theta is this signal amplitude here. And I should say that this is true or there's a phase transition after which this is true, and that phase transition is a relationship between theta and sigma. So you can think as long as your underlying signal amplitude is large enough, then we get this recovery guarantee. Okay, and then we, in our previous work, studied this same unweighted PCA problem, but with heteroscedastic data, and we got a similar guarantee. It's, again, a quotient of two functions, and we'll show later more explicitly what these functions look like. And this ratio is, in a similar way, would go to 1 without noise, but is something less than 1 otherwise. Now, this is studying unweighted PCA, and a result of this analysis that we did was to see that actually the recovery guarantee is optimized when the data are homoscedastic, if all the noise variances were the same. So it was a natural question for us to ask, is there a way to change PCA so that we could handle the heteroscedastic data and not be, get these suboptimal results in the heteroscedastic setting? And so that's what I'm going to talk about for the rest of today. So when we're weighting PCA, in this case, oh, yes?
No question. A lot of times people will just divide their columns by the variance, just to make it all homoscedastic. I take it that's throwing away information and it's not optimal, or what's...
No, that's an excellent question. I'm going to actually talk quite a bit about that strategy compared to what we find as the optimal strategy. The question was if we just divide every column by, or multiplied by 1 over the noise variance, then we have some kind of whitening, and we could use that. I'll talk about that quite a bit. Thank you. Are there any other questions?
Do we assume that we have access to the noise variance?
Yes, we assume we have access to those noise variances. And in a minute here, I'll talk about what we assume we know. Yes, please.
So are you assuming that the eigenvectors are distinct?
No.
So earlier in your formula, then the n goes to 0, or it could be...
Yeah, so this one right here is for distinct. You'll see another formula later that makes it a little better, but you could think of this either as distinct or as the projection onto all the ones with the same eigenvalue. Okay, so we're going to do a particular type of weighted PCA. Since every column in our data set has a different known noise variance, we're just going to weight by column. And so we'll have a weighted PCA objective where we've inserted these weights gamma. And of course, if I have these gamma weights inserted here, that's just equivalent to finding the PCA solution for the weighted data matrix. So all I have to do is weight every column, apply PCA, and I have weighted PCA output. So the algorithm that does exactly that is the one we're going to analyze. And I'm going to assume, though this isn't necessary, that for each group I mentioned before of different noise variances, we'll just weight all those data points the same way. And we'll call those weights as W1 through W capital L. Okay. So it turns out that this is the strategy that makes the most sense, but it's not necessary. All of our analysis applies to other settings as well. Okay, so now let's look at kind of the things that we assume we know, and then ask the question, how do we weight PCA, and what are the asymptotic recovery results of weighted PCA? So we say we know, of course, the number of samples per dimension. We're going to assume we know the noise variances, and which samples have which noise variance. Okay, which ones are high quality, which ones are low quality. And then the recovery will also be in terms of the subspace amplitudes, though we also have recovery guarantees for those. So given that, we can use a kind of plug-in estimator for the other recovery guarantees.
So,
Yes?
Laura, maybe anticipating what will come next, I can think about a signal that is strong with respect to the first N1 samples, but it's very weak with respect to the other ones because they have much higher noise level. So some of the weights are going to be 0, or?
That's another good question. So the question was, will some of the weights instead be 0? And I'll just start out by saying that the two suggestions that have now been mentioned are very common and natural choices. And really what our work is going to ask is there an optimal choice? And I'll show you that sometimes throwing away the data is nearly optimal, and oftentimes inverse noise variance is nearly optimal, and our results give exactly those answers. Okay, so like I said, these are common choices of the weight, but can we understand what the optimal choice is? Before I show you the theory, I'm going to show a couple of plots just to get an idea of what happens to weighted PCA in simulation. Okay, so in this simulation, we're going to have one sample per dimension. P and N are the same. We have a 2-dimensional subspace. We're trying to recover 2 different principal components. And then we have some data, about 20% of our data, that has noise variance 1, and 4 times that data has 4 times that noise variance. So a lot of data that's very noisy, and a smaller amount of data that's less noisy. These are the kind of plots we see in that context. So let me tell you what you see here. On the y-axis is the inner product between the PCA, the principal component recovered from weighted PCA, with the underlying principal component. And then on the x-axis is the weight. So we're just sweeping a weight between 0 and 1 and having the other weight be 1 minus that. In the case of 2 sets of data, we can do that without loss of generality. And we see, this is in a moderate sample regime, that we get some behavior here of an the inner product for the first principal component, here the inner product for the second one. With a smaller amplitude, we get a lower recovery. And this line is for uniform weights, meaning unweighted PCA. And this line is where inverse noise variance weights are. And then, of course, throwing away data would be, here, I guess we wouldn't do that because that's throwing away the cleaner data. But this would be throwing away the messy data. And in this case, it looks like that's not something we want to do. Then over here is the same plot, but at a higher number of N and D. And so these simulations are, I'm showing you just to show that they seem to illustrate that this concentrates in high dimensions. and that if it converges to some particular curve and we can predict what that curve is, then we could try to optimize that curve in order to pick the optimal weights. And that's exactly what we'll do. We'll first show the predictions of that high-dimensional behavior, and then we'll optimize that asymptotic curve. Yes?
Are you trying to find optimal weights just as a function of the sigmas, or also as a function of the fractions of each?
So I'm going to allow it to be a function of anything in the problem. Okay. Yes?
Again, although in this example, theta 2 is still large.
That's
above
true.
the phase transition of the,
Yeah,
the weaker.
yeah. And I'll show some other examples that might clarify or, speak to what you're interested in. Okay, so now that we have this understanding of what I'm going to do, I'll start with the first theorem. So this is a theorem for recovery of the principal components. Here's the term that I'm interested in. And we're going to let the sampled to dimension ratio go to C as n and d go to infinity. And these proportions of data go to some proportions p sub l. Then we see that the ith principal component converges. So this is what was discussed earlier. Here, if I have multiple components with the same singular value or the same amplitude, as I'm calling it, then I would project onto the ones in the underlying subspace that all have that same amplitude. And that converges to this function, which I'm going to denote as Ri of u, the recovery of the ith component u. And if the two subspace amplitudes are not the same, then it should be orthogonal, okay, in the limit. So this holds. Again, we have a phase transition when this quantity is strictly positive. And this A, B, and beta are defined in this way. We have two rational functions, somewhat simple rational functions of x, the weights, the proportions, the noise variances, and the signal to, or the sample to dimension ratio, and the amplitude. So instead of trying to explain this or try to get you to understand it very carefully, I thought I would show just an example of this with one choice of weights. Is there a question first?
Yeah, I'm assuming that one motivation is that you want to, given data, find how to weight it. But this tells you that the weights depend on the signal strength, which you don't know.
Right. The weights depend on the signal strength and the noise variances.
So the noise levels somehow know.
Right. So the signal strength is something that seems less likely that you know. Yeah, I agree. And later I'll show you the explicit form of it. I won't today show our asymptotic guarantees for the amplitudes. I have them in backup slides if someone wants to see them. But those guarantees for some choice of weights give us a bias correction term. So we have a good enough estimate of those from like unweighted PCA that we should be able to recover them. Okay, so let's look at an example of this theorem. In particular, when we use inverse noise variance as our weights, okay? So you'll notice, here I just have some weights, so I'm weighting each group by W. Those weights can be chosen however you like so far, and this analysis will hold. So I'm going to choose that W to be 1 over sigma squared. I'll also multiply by the average noise variance just to have something that looks familiar at the end, okay? So if we just plug this one in to our A and B, we see that we have some nice cancellation with sigma squared. We get a much simpler form of both A and B. And then the root of these two rational functions is also straightforward to calculate. And if I plug these in then, when A of beta is positive, which was the phase transition I mentioned, we have just this form right here, which you may recognize from the earlier slide, which is exactly the homoscedastic setting for PCA, where all of them have the average noise variance. Okay. So indeed, when you just plug those weights in, you get something that matches previous results.
Where here is the fraction of each kind of each signal strength? Is that theta? No.
No, theta is the amplitude, but do you mean like the number that is high quality, the number that is low quality? Yeah. So in this case, I am weighting using inverse noise variance, right? So I'm ignoring that. And when you plug that into here, and this will no longer depend on L, it comes out of the sum, and this sums to 1. So that's why it disappears. Does that help? Okay, so this is what the theorem says when our weights are inverse noise variance. So now let's look at the way these asymptotic results relate to the simulations I showed earlier. I've now added that curve on here in the orange dotted line, and we can see that it lines up nicely with the simulations, especially as these numbers grow. Okay, so now the game will be to try to optimize this recovery curve over W to pick the best weights in order to get the best weighted PCA recovery. Okay. So far, I have just given you the asymptotic recovery of unweighted PCA. We did that in prior work, but it's also clearly a case from the theorem I just showed you. And so then also we have the asymptotic recovery for weighted PCA, and we will now try to choose the weights by maximizing that recovery curve. Okay, so if you take that curve and you look at where it's optimized with respect to W, it turns out that this is what you get. It's a very simple form that the weights should be 1 over the noise variances times this other term that has the unknown amplitudes in it. Okay, it's 1 over the amplitude plus the noise variance for each column. Okay, and because the amplitude is there, that means that for every component you want to recover, you have to use a different weighting on the data, right? So if you knew theta 1, you would use that to recover the first component, and then you'd have to use different weights to recover the second component, and so on. But what is very interesting is this expression does not depend in any way on the samples per dimension or other things besides the noise variance and the signal amplitude. So that seemed like an interesting conclusion to us. So if we look at this expression in terms of other things we might consider, like the inverse noise variance, for example, we see that as the signal-to-noise ratio increases, this will range between the inverse noise variance, if the signal-to-noise is very, very high, and the square inverse noise variance, if the signal-to-noise ratio is very small. Okay? But in particular, neither one of those is ever optimal. The optimal choice of weights is somewhere in between. And also in particular, the optimal weights will downweight the noisier samples more. And so that's why we'll see in some cases where the noise is very, very large, actually using binary weights is also close to optimal. Okay, so if we look back at our example one more time and now plot these optimal weights on the curve, we see, two different green lines, one for each of the two components. And in this case, they're not exactly the same as, but very, very close to the inverse noise variance weights. Okay. So let's go through a few different numerical results now. I'm going to basically showcase to you what types of conclusions we can draw from these, from the theorem I showed you earlier, and these asymptotic optimality of the weights I showed. So in this case, I'm going to show two case studies. Now we have 10 samples per dimension, and I'm just going to look at one component. It doesn't matter in some sense which one it is, but it has an amplitude of 1.5. And then I'm going to sweep the proportion of samples that are in the cleaner set and the proportion in the noisier set. The cleaner one has 0.1 and the noisier has 1, so still not greater than the amplitude, but a lot closer. So first, if we have P1 and P2 equal to 50%, okay, so I have just half good data and half bad data, then we actually see exactly the setting I was mentioning. As we increase the weight, we get a better recovery, and actually throwing away the noisy data gives nearly optimal recovery. Now, in this case, that is because we have a lot of clean data, right? 50% of our data has this very small noise variance. If instead we looked at the setting where we have a very small amount of clean data, or data with the small noise variance, and most of it is noisier data, we get a curve that looks quite different, has a very interesting shape. And in that case, actually throwing away the noisy data would result in much worse recovery. And we have our optimal and inverse noise variance weights still near the top of this curve. There are also other cases which you can find in our paper where the inverse noise variance weights are, somewhat below the optimal weights. And so it basically depends on, playing with these things like the samples per dimension and the relationship of the amplitude to the noise variances. Okay, so I was just pointing out here that, of course, the optimal weights are the same because when the proportions change, the weights didn't change, but the recovery curve is quite different. Here's another conclusion that we could draw using the theory that we have. So here I'm showing a data set where I'm running PCA on it and letting the proportions change. So over here I have only data which has a very small amount of noise, in this case again 0.1, and on the right hand side I have only data that has a very large amount of noise, 3.25 with a 1 amplitude. So it's significantly higher than the component amplitude. And in this case, you can see that the recovery for both inverse noise variance and optimal weights is much, much better than PCA. Of course, that's intuitive because we know PCA is not robust to outliers. And in this regime where we have many, many of the noisier points, the optimal weights do slightly better because they downweight those noisy points much more aggressively. Here's another plot that shows the recovery of the principal components, but in a heat map as we changed sigma 1 and sigma 2. This one is for unweighted PCA. This is from our prior work. And we can see that, if either one of the noise variances in two groups is large, then PCA will not do a good job of recovery. But when we use inverse noise variance or optimal weights, we actually get a very nice curve with the opposite direction. So if any one of these two noise variances is small, then we can downweight the other one, well enough in order to get a very good recovery. So the optimal weights are, you can see, sort of slightly better, especially out in the regime where you have a very large, one of the noise variances is very large. one more plot that I found especially interesting and intuitive after we thought about it, but it took some time. So this one, we look at the impact of adding noisy data. So we have some clean data, okay, and I'm just going to fix that amount, right? I have some data which has noise variance 1. And then I'm going to add data to that data set, right? So I want, as I add that data for the principal component recovery, to get better, right? That's the goal. And on this top plot, I see uniform, inverse noise variance, and optimal weight. So this is unweighted PCA, inverse noise variance, and the optimal that we showed. So we can look first when the noisier data has the same noise variance. We see in all cases it's this brown line, and as we get more data, our recovery improves. Okay. But when we have higher noise variance, especially in this regime where it's much higher, then certainly, as may be intuitive at first, for the uniform weighting, we get worse performance, and slowly, as we have much more data, we improve above the original performance at some point. But when we have inverse noise variance weights, we have the same curve. So at first, adding some noisier data does do detriment to this weighted PCA. But for the optimal weights, that curve will never go down because it will weight those very aggressively such that we always get improved recovery. Okay, so are there any questions on these different numerical results before I sort of say a last couple of words? Okay, good. So one of the last things I wanted to say was in this process, we thought about the heteroscedastic PCA problem from a variety of different perspectives. And we considered what would the maximum likelihood model be if we had normal weights and normal, sorry, I shouldn't say weights here, normal z instead of just arbitrary zero mean zero variance 1, and then normal noise, but of different noise variances, right? So it's very interesting to see that the maximum likelihood estimator actually looks like this. So, if we didn't have these different noise variances, this would be some diagonal matrix independent of the data point, and we could pull it out, and we would see our covariance matrix, and we would just need to compute its principal components, right? But this matrix, has A to I here, so it depends on the particular noise variance that's been added to that data point. And so this is, if I replace this matrix with some gamma, this is an interesting looking but non-convex problem that can't be solved with PCA. And we're very interested in studying this further. And then not only that, but the entries look very close, highly related to the optimal weights that we found in our analysis. So if anyone has ideas on how to solve this, we have some and we'd like more. Yes, please.
Can these ideas be adapted and used for like linear mixed models?
Linear mixed models where I have not data coming from one subspace but from multiple.
Well, what I'm thinking is that the samples are no longer IID, right? There's some relation between them, right? So in that setting, do you think you could adapt what you're doing to kind of do robust inference in the case of?
So yeah, that's a great question. So I think that we can adapt some notion from the weighting method and the algorithm, but I'm not sure that the analysis would apply to that setting. I mean, I think it's actually quite important that this is IID in order to do the analysis that that David did. So he could certainly answer that better, but okay. Okay, so in conclusion, I showed an analysis of the asymptotic performance for weighted PCA and high dimensional and heteroscedastic data. We can use that prediction in order to find weights that optimize that recovery. And those weights turn out to be quite simple, very interesting, and allow us to draw a lot of really interesting conclusions about adding noisy data and having certain proportions of data in the particular case where you want to do principal component analysis. We could see how it changes the impact of a variety of different data properties. So if you're interested in looking more at the analysis and the other experiments we have, the paper is here on arXiv. Thank you for your attention. Let me know if you have more questions.
Questions?
So it seems that the optimal weights depend on how big the signal is and how big the noise is. Mm-hmm. Are there ways to estimate how big those things are in order to get weights?
Yeah, so if we knew which data are which quality, at least, then maybe we could estimate the noise variances. Though, needing to estimate those jointly is an interesting question. I don't know if just having the assumptions that we've made can give us an estimate of the noise variance. I'm not sure. But if we had the noise variances, there are clearer ways to estimate the signal amplitude. So, I have, if you would like to see, I can show a slide later that has the recovery of the amplitudes. And it, as in the homoscedastic setting or the now classical high-dimensional PCA analysis, there's a bias on that recovered singular value or amplitude, a positive bias, but you can compute it. So if you run PCA, then you know what the bias is, at least asymptotic bias, but you could debias in that way. Yeah. Yes?
I'm a little surprised by the look of the optimal weight. So it's 1 over sigma squared and 1 over theta squared plus sigma squared, right?
Right.
So they're not in this. So the inverse variance would just be 1 over sigma squared, right?
Right.
So I'm surprised that they don't have the same unit in a sense. If I were to reason like a physicist.
Yeah, that's an interesting point.
And they're not necessarily. So in some of the examples you gave, the inverse and the optimal were not too far from each other, but it would seem like I don't see why they should be close to each other.
Sorry, can you say it again?
So in some of the examples that you gave, the two were near each other, the optimal and inverse were close to each other, but in the expressions they're not really close to each other.
Because, yeah, okay, here, I understand. Because, for example, in these settings, well, this one isn't as good, but let's say here, these are quite different, right? So those values would be also very different. Is that what you're saying?
No, I'm saying like the inverse and the optimal are nearby, right?
Yeah, so this one, for amplitude 16, we have either 1 over 4 or 1 over 4 times 1 over 20. Those are very different things, is what you're suggesting. Am I right?
I'll take off then.
Okay, sorry. Let me just say that that's an interesting question, and as you were saying, thinking like a physicist, thinking of the unit. So that I haven't thought about, and why we would need to incorporate these two different things that could be on very different scales. Maybe my best intuition comes from this plot that somehow the inverse noise variance weights alone aren't aggressive enough, and so if you think as SNR changes, this never gets worse than square inverse noise variances. So in some sense, it is still on the same scale as the amplitude changes. And that's in part because we can always scale the weights. If we scale all the weights by the same value, we get the same PCA output. Yeah?
You actually observe things a little bit like that when you look at Poisson models with over-dispersion. So if you look at count models with over-dispersion, you start getting this mix of the means and the variances kind of mixing together, right, towards looking like a negative binomial. So in those settings, you see somewhat of a similar phenomenon.
Interesting. Now I'll have to ask you more about it later.
Okay, let's thank Laura again.
Thank you.
And we'll have a 5-minute break.